Hello everyone! Today we will start learning about three-phase transformers. In modern power systems, three-phase power supply systems are adopted. Therefore, three-phase transformers are widely used in power systems. When a three-phase transformer operates symmetrically, any one phase of the three-phase system can be used for analysis. Previously, we have analyzed and studied single-phase transformers. The analysis results of single-phase transformers are fully applicable to three-phase transformers when they operate symmetrically. Therefore, in three-phase transformers, we will only discuss a few special issues of three-phase transformers. In this lesson, we will mainly introduce to you the magnetic circuits and electrical system of three-phase transformers. You are required to master the following two parts. 1. Master the struggle characteristics of three-phase group transformers. 2. Master the magnetic circuits structure and characteristics of three-phase core transformers. 3. Understand the circuit connection methods of three-phase transformers and the markings of the beginning and end terminals. First, let's analyze the magnetic circuit system of three-phase transformers. The magnetic circuit system of three-phase transformers can be divided into group transformers and core transformers, according to the structure of the iron core. A three-phase group transformer is composed of three identical single-phase transformers, as shown in the figure below. From the figure, it can be seen that each phase magnetic circuit of the three-phase group transformer is independent. The main flux of each phase passes through its own iron core, forming a closed loop. Therefore, the magnetic circuits of each phase are independent of each other and not related. When a symmetrical three-phase voltage is externally connected to the primary side, the main flux of the three phases is symmetrical. Since the magnetic circuits of the three phases are symmetrical, the no-load currents of the three phases are also symmetrical. The core transformer involved from the group transformer, as shown in the figure below. In figure A, in fact, it is a three-phase group transformer combined together. According to Kirchhoff's first law of the magnetic circuit, the magnetic flux in the middle core column is zero. Therefore, to save materials, the middle core column is removed, thus forming the shape of figure B. Since figure B is a multi-sided three-dimensional shape, it is inconvenient to produce. To facilitate production, it is made into the flat shape of figure C, commonly known as the three-phase, three-core column transformer. This is the evolution diagram of the three-phase core transformer structure. Obviously, the core transformer has the following two characteristics. 1. Since the main flux of each phase needs the flux of the other two phases to close, the magnetic circuits of each phase are interrelated and not independent. 2. When a symmetrical three-phase voltage is applied to the primary side, the main flux of the three phases is symmetrical. Since the magnetic circuits of the three phases are not symmetrical, the no-load currents of the three phases are also not symmetrical. We generally take the average value of the no-load currents of the three phases for analysis and calculation. The no-load current of the three-phase core transformer is asymmetrical. So, the size relationship of the no-load currents of phases A, B, and C needs to be determined. How is it determined? We can combine the paths of the magnetic circuit and Ohm's law of the magnetic circuit for analysis. From the paths of the magnetic circuit, the path of phase B is the shortest, while the paths of phases A and C are equally long, and longer than that of phase B. Therefore, the magnetic resistances of the three phases are not equal. According to Ohm's law of the magnetic circuit, it can be known that in any closed magnetic circuit, the magnetomotive force and magnetic pressure should be equal. Since the number of turns and the magnetic flux of phases A, B, and C should be constant values, the no-load currents of phases A and C are equal and greater than the no-load current of phase B. That is, the no-load current of phase B is the smallest. However, when the transformer is under load, the no-load excitation current is very small compared to the load current, so we consider the three-phase currents to still be symmetrical. Next, we will compare the group transformer and the core transformer. The group transformer is easy to transport and has a symmetrical magnetic circuit. Its disadvantages are that it consumes more materials and occupies a larger area. The core transformer has the advantages of consuming less material, high efficiency, small footprint, and simple maintenance. Its disadvantages is that its magnetic circuit is not symmetrical, and it is inconvenient to transport. Obviously, the advantages of the group transformer are the disadvantages of the core transformer, and the disadvantages of the group transformer are exactly the advantages of the core transformer. Since the three-phase core transformer has the advantages of less materials consumption, high efficiency, small footprint, and simple maintenance. It is widely used in power systems. Three-phase, three-column transformers are usually used, but when the rated capacity of the transformer exceeds 100 MVA, if a three-phase, three-column transformer is used, its structure is too high, making transportation difficult. To reduce the height, an additional yoke iron core is usually added on both sides, called a three-phase, five-column iron core. The winding is placed on the three middle core columns, and the side yokes serve as branch magnetic circuits. For ultra-large capacity transformers, three-phase group transformers are usually used, which are easy to transport. 2. The electrical part of the three-phase transformer. There are two connection methods for the circuit of a three-phase transformer. 1. Star connection, where the ends of the three windings on the same side are twisted together into one point, forming a neutral point. The three ends are let out of the oil tank through bushings. If the high voltage side is connected in a star shape, it is denoted by a capital Y. If the low voltage side is connected in a star shape, it is denoted by a lowercase y. 2. Delta connection, where the end of one winding on the same side is connected to the start of another winding, forming a closed loop in sequence. The three ends are then let out of the oil tank through bushings. If the high voltage winding is connected in a delta shape, it is denoted by a capital D. If the low voltage winding is connected in a delta shape, it is denoted by a lowercase d. For example, a three-phase transformer with high voltage windings connected in a star shape and low voltage windings connected in a delta shape is denoted by YD. In our country, the commonly referred to three phases are A, B, C phases, with the starting terminals denoted by A, B, C, and the ending terminals denoted by X, Y, Z. So, how do we distinguish between high, medium, and high voltage levels? Usually, the high voltage side is denoted by capital letters. The medium voltage side is denoted by capital letters, with the subscript M, and the low voltage side is denoted by lowercase letters, as shown in the table below. In this table, it is clearly shown that, for a three-phase transformer, the starting terminals of the high voltage side are denoted by A, B, C, and the ending terminals are denoted by X, Y, Z. The starting terminals of the low voltage side are denoted by A, B, C, and the ending terminals are denoted by X, Y, Z. The starting terminals of the medium voltage side are denoted by AM, BM, and CM, and the ending terminals are denoted by X, Y, Z, with the subscript M. A, B, C phases are the names of the three-phase windings in our country. In the world, the commonly referred to the three phases are U, V, and W phases, with the starting terminals of the three-phase windings denoted by U1, V1, and W1, and the corresponding ending terminals denoted by U2, V2, and W2. So, how do countries around the world distinguish the high voltage side from the low voltage side windings? 1. For a double winding transformer, the high voltage side is distinguished by adding the number 1 in front of U, V, W, and the low voltage side is distinguished by adding the number 2 in front of U, V, W. 2. For a three-winding transformer, it is the same. The high voltage side is distinguished by adding the number 1 in front of the letters. The low voltage side is distinguished by adding the number 3 in front of U, V, W. The medium voltage side is denoted by adding the number 2 in front of U, V, W. The table below shows the international standardized U, V, W three phases, their corresponding starting terminal letters, and the form of expression for the ending terminal letters. you can carefully browse through this table to understand it better. Earlier, we introduced the International Standardized Three-Phase Transformers and the expression of the starting and ending terminals. So, how do we use characters to represent the high, medium, and low three-phase windings? Let's take phase A as an example to explain. The U phase of the high voltage side is denoted as 1U, 1U, 2. The U phase of the medium voltage side is denoted as 2U, 1U, 2. The U phase of the low voltage side is denoted as 3U, 1U, 2. In this lesson, we mainly introduced the magnetic circuit system and electrical system of three-phase transformers. In the magnetic circuit part, we mainly introduced the structure of group transformers and core transformers and compared their characteristics. In the electrical system, we introduced the circuit connection methods of three-phase transformers and the characters for the starting and ending terminals. We also introduced the different expressions in our country and internationally. I hope everyone revises seriously after class. That's all for today's lesson. Thank you, everyone.